Okay, we're going to look at the second video in this short series devoted to this very interesting routine entitled Proof That Opposites Attract. We're going to ratchet up the sophistication a little bit to the intermediate level. Okay, now it is true for this one, you actually do need 6 red and 6 black. For the basic one, you could have any number of red and black as long as you have equal numbers of each, okay? But here it's actually important that we have a total of 12 cards, and we'll explain exactly why that is the case, okay? So what we do here is we, as before, have the spectator randomly stack these together. Maybe they'll put the red on the black. That's just fine, okay? And then we're going to Klondike shuffle the cards, okay? So that's what we did in the basic routine as well. In fact, I'll probably tell you where we deviate. Okay, so that's the same. Now, in this intermediate case, we're going to perform the Charlier shuffle. Okay, now I do have a separate video on the Charlier shuffle. This shuffle is worth mastering if you're at all interested in math card magic. Okay, so this is where you push off any number, and then from the bottom you deposit some on top. Then from the top here you put some on the bottom, and the rest go on top. Okay, so that's called the Charlier shuffle. Now we're going to ask the spectator to tell us when to stop dealing. Maybe they'll say stop there, and that's just fine. And now what we're going to do is we're going to perform a rosette shuffle. You just spin those, bring those together however they will. Okay, so it's a bit of a mess actually. Okay, and then from there we're going to perform a mange, over, under, or under, over. And the spectator can decide this. So maybe they'll ask for an under, over, under, over, under, over, under, over, under, over, under. Okay, that's a mange. Okay, and now what we're going to do, and that's the same as the basic case, so we haven't, that's not different. And then we deal out into 2 piles, which we've done before with random stacking decided by the spectator. That's really important. Okay, and maybe they'll ask for right on left. Now you can actually do as many of those as the spectator calls for. You really can. You can do 5 million of them if they have the patience. Okay, but what we're going to do beyond 2 piles, we're actually going to deal into 3 piles with random stacking, left to right or right to left. Maybe they'll go left to right. That's just fine. Maybe we'll do one more of those. Okay, 3 piles. Okay. Maybe they want left to right again. That's just fine. They can choose either direction. And then we're going to deal into 4 piles. 1, 2, 3, 4. This is crazy. Think about how these cards are being moved around. Oh, so left to right, right to left, left to right. Okay. So that's just fine. So you can do as many of those as you like, from left to right or right to left. But we can also do something called a leapfrog stacking, which is a really fun one. So this is where you go from left to right or right to left, but the cards jump over their neighbors. So for example, the leapfrog stacking from left to right would look like this. This pile leaps over its neighbor, lands there. This one leaps over its neighbor, lands there. And then we randomly stack these, however the spectator calls for. Okay, so you can do that from either direction, and you can do as many of these as you like. Maybe they'll do a leapfrog from right to left. That's fine. You leap over the neighbor, leap over its neighbor, random stacking here. Maybe they'll go like that. Okay, and we can even deal into 6 piles. 6 piles. Okay. And you can stack from left to right, just normally, right to left, normally, or leapfrog stacking from left to right or right to left. And you can do as many of all of those shuffles as you like, or the spectator asks for. Okay, so maybe we'll do a left to right leapfrog, kind of a fun one to do. Okay, with random stacking here, of course. Maybe they'll go like that. Okay, so that's all new. dealing out into 3 piles, 4 piles, 6 piles, and then with this leapfrog stacking, that is brand new. We did not do that in the basic routine. Okay, and then at this point, we're finally going to confirm that indeed opposites attract. Oop, seems to be the case so far. Yep. Yes, indeed. We have just confirmed the truth of this aphorism. Opposites do, in fact, attract. Okay, so let's look at some of the mathematics for this one, because there's some, of course, some new elements here. Okay, now it does use the same principles, but let me just kind of explain that. I like to have each of these kind of self-contained, where if you didn't watch the basic one, you can still figure out what's going on with the intermediate one. Okay, so we'll explain everything here. Okay, so you have 6 red, 6 black. That's important. As I mentioned, you can stack those as blocks of cards. That's important. Okay, and then what we did from there was we did a Klondike shuffle. Well, think about what that's going to do. The top 6 cards are red, the bottom 6 are black. So here, if I take the top and bottom, this will be a red, black, red, black, red, black pair there, red, black pair here, red, black, red, black. What have we done? We've created a cyclic packet. It alternates in color. So don't worry about the card values. We're just focused on color here. Okay. So is it true that it alternates in color? Well, it certainly is the case. Red, black all the way through. In fact, we would call this a 6 cycle with cycle length 2. Now, the cycle length refers to how many cards it takes for a certain pattern to repeat. And then the number of times that pattern repeats, that will be the number we put in front of a 6 cycle with cycle length 2. Okay, so it's a 6 cycle because it repeats these pairs of cards 6 times. Okay, so this is a 6 cycle with cycle length 2. Well, anytime you have a cyclic organization of a packet of cards, the Gilbreth principle can be applied. So what is the, and now before we do that, I almost forgot, I apologize. Before we do that, let's talk about the Charlier shuffle, okay? So the Charlier shuffle is equivalent to just cutting the cards at some location. Well, let's focus on that first. So if you have a cyclic construction and you cut the cards, does it undermine the fact that it's alternating in color? Well, it doesn't. Now, one thing it may do is it may change, like, for example, I can actually, quote, cut this one to the bottom. So now it's black, red, black, red, black, red. Well, that's still cyclic, okay? So an ordinary packet cut preserves cyclic packets. Now, the Charlier shuffle, and I have a separate video for the Charlier shuffle if you want to look it up, is actually equivalent to just cutting the cards. Okay, so this is where you push over any number of cards. So the little mantra I repeat to myself is top to bottom, bottom to top to bottom, bottom to top. Okay, so these go over. So top to bottom, this will be the bottom now of the new packet. And then from the bottom, you push over any number, deposit those on top of the cards in your left, and then some top cards to the bottom, some bottom cards here on top, and then the rest can go on bottom. Okay, so that's a Charlier shuffle, and it truly is equivalent to just cutting the packet at some location. Therefore, it preserves, and we can just confirm that really quickly, it preserves cyclic arrangements of packets of cards. Okay, so it's still alternating. Okay. Now we can perform the Gilbreth principle, and so here you can deal out any number of cards. So here are the 2 actions for the Gilbreth principle to apply. First, you have to be aware of some kind of cyclic organization, which we have here, and then you deal out any number of cards. So maybe we'll do 6, maybe we'll do 7 this time, and then you put the rest here. And now you bring these together using a riffle shuffle. Well, what's a riffle shuffle? Well, technically a riffle shuffle is where you have a packet of cards, you break it roughly in half, and then you just let the cards fall left, right, however they may. Okay. Now, this rosette shuffle, mathematically speaking, is equivalent to doing that. It accomplishes the same thing. So this is, quote, like riffle shuffling the cards. Okay. Now, those didn't interlace all that well, but it doesn't actually matter how they interlace. The Gilbreth principle now applies. And what's the conclusion of the Gilbreth principle? Well, it says that if you take off cards having the original cycle length, which was 2, so you take them off as pairs, each pair will consist of 1 of each color. Okay? It looks like I didn't mix them very well. Sorry about that. Okay, so we got, as far as I can tell, yep, we got right back to the cyclic. In fact, that's not very satisfying, so let's do that again. We'll do the, it truly doesn't matter how many you deal out. I think I had most of these slide under the others. Okay, so let's do that again, just so we can get something more interesting. Okay, there you go. Maybe that will be a bit more interesting. Okay, and so the conclusion of the Gilbreth principle says that as you take off cards in pairs, you are guaranteed one thing, and only one thing, that each pair will consist of a red and a black in some order. Now, technically, we won't know the order. See how it changed the order now? Once I mixed it a little bit better. Okay, so there we go. Oh, now we almost went to the, oh no, that's not too bad. Okay, so we got black, red, then red, black, red, black, red, black, red, black, black, red. Okay, so that's a more typical outcome for a Gilbreth shuffle if you start with an alternating packet of red and black cards. Okay, so anyway, that's the Gilbreth principle being applied, which is a wonderful principle. Okay, now this particular organization of the cards, now this is brand new. This is important. No one out in the literature is aware of anything I'm going to tell you now unless they've actually watched and read some of my materials that I've put out there in the last few years. Okay, so I call this an AMP. AMP stands for adjacent mirrored pairs. Pairs of cards taken from the top or from the bottom will have the characteristics that we want. Namely, we want them to be of opposite color. Okay? So these two have that characteristic, or of opposite color within the pair. The same thing here. Well, it ends up that if you have, quote, an AMP and you perform a mange shuffle, that's the over, under, over, it converts it to a mirrored structure. Okay, so why don't we do an over, under this time? Over, under, over, under, over, under, over, under, over. Okay, so what that does then, it puts them in a mirrored relationship relative to one another. What does that mean? Well, the word mirrored was chosen for an obvious reason, because we say the position of this card here is in a mirrored relationship to the one way over here. Well, look, they're of opposite color. If you come in one from the top, one from the bottom, they're of opposite color. Do that again and again and again all the way to the middle, they're of opposite color. So the cards that we had in pairs just a moment ago, before the mange shuffle was performed, they're now in a mirrored relationship relative to each other. Okay? Now, once you have a mirrored organization of any packet of cards, the stay stack principle can be applied. And I have a video that very carefully goes through the stay stack principle. So how does that principle work? Well, it allows you to deal out the cards into different numbers of piles with stacking from left to right or right to left, and even this leapfrog stacking I'll show you in a second. But you can do that into any number of piles if that number of piles is a divisor of the packet size. Well, why did we choose 12 for our packet size? It's because of all of its wonderful divisors. 2, 3, 4, 6 divide evenly into 12. Okay, so what that means in particular is we can deal out the cards into 2 piles with random stacking left on right or right on left. It's still going to be mirrored. Okay, so we'll do this again. Maybe right on left. Okay, very good. In fact, why don't we just show you that it's still a, quote, mirrored packet relative to the card characteristics of interest to us. So here are the mirrored mates. Top one and the bottom one, they're of opposite color. Come in one, opposite color, all the way to the middle. Okay, now 2 is not the only divisor of 12. 3 is as well. So we can deal into 3 piles with random stacking from left to right or right to left. It doesn't matter. And you can do as many of these as you like. You can do them forever. Well, not forever. You won't finish the routine. You can do thousands of them if you like, or just one. Okay, so it's still mirrored. 4 is a divisor of 12, of course. So you can divide into 4 piles with random stacking from left to right or right to left. Or what I've discovered is this leapfrog stacking. Now, I don't know if anyone's aware of this. I haven't seen it anywhere. So this is where instead of just stacking left to right, systematically, you can do a leapfrog stacking. So this one leaps over its neighbor, lands there. This one leaps over its neighbor, lands there. And then you can do random stack here. Okay? So this leapfrog stacking will not harm organization of the packet. Now 6 is also a divisor of the packet size. So you can deal out into 6 piles. You can stack them from right to left, left to right, or leapfrog. Why we do leapfrog? Just because it's so much fun to do. Leap over its neighbor. This one leaps over its neighbor. Random stacking here. Okay. And let's just confirm that, yes, indeed, it's still mirrored. Okay. So is it still mirrored relative to opposite card color? It is indeed. You come in one, all the way to the middle. Those are of opposite color. Okay. Now, as was the case for the basic one, if we now go ahead and Klondike pairs to the table, it's guaranteed to pull off these very mirrored pairs that we're focused on here, right? So we're guaranteed to confirm this idiom here that opposites attract. So do a Klondike like that, this. And by the way, in terms of surprisal value in the field of information theory, this is highly unlikely to happen by chance alone. It really, really is. Okay, so if you calculate the surprisal value for this, it's really pretty high. Okay, so this doesn't happen by chance alone very often. Okay, so we've supposedly confirmed the truth of this claim that opposites attract. Okay, very good. So that is the intermediate case. So the next one up will be the advanced routine, and this gets pretty wild but fun at the same time. So thank you for watching.